Good morning, everyone. It's very nice to see you after 1 week. So starting from this week, we will learn K-means clustering. So recall until now, we have learned two models, naive-Bayes model and K-means model. If you still remember, both of those two models actually belong to supervised learning. Then today, our topic K-means clustering is an unsupervised learning algorithm. So let's try to look at some practical problem we will deal with. So now we have a simplified more customers data set with some attributes. We have three attributes or three features here. Age, income, the income is in thousands units, and expense score. Here expense score is just some values in the continuous range 1 to 100, representing whether the customer has low spends or high spends. We have these three attributes, and as we can see in this table, now we have 20 data points. Basically, that's 20 customers, right? So each customer has these three features, and you may already notice that this data set does not have label, only attributes, only three attributes, but no label is provided. So that means if we want to use this data set to learn something, we cannot learn the relationship between the attributes and the correct outputs, because we do not have correct outputs here. Then what can we learn? So let's consider this question. Could we try to cluster the customers based on their characteristics to determine, for example, the targeted advertisement, and then make the marketing budget more efficient? So now our task has transformed to we try to cluster the customers instead of learn some relationship between the features and outputs, because we don't have any outputs here. Cluster means that actually we don't need to do some prediction about the labels. Instead, we only want to group all of the data points possibly into some similar groups. This is the clustering, and clustering is just grouping the things into some natural categories when no class label is available. So for example, for this data, possibly we can try to group all the data points into three clusters, because it seems that these three natural categories can just separate these data points. And for this one, we set the number of clusters to be 7, but possibly this is not so natural, because as we can see, all of the groups, they just collapse together. But this is the idea of clustering. Clustering basically is just grouping, but in terminology, we call it clustering. Why should we do the clustering? First reason, because sometimes we just don't have the labels. Because labeling a large set of data samples can be very costly. You possibly need some humans and even some expert humans to do the labeling. Of course, that costs you so much time, manpower, and possibly money, right? Because you need to pay the humans to do all these labeling tasks. So it's just not practical to acquire a large amount of labels. But actually, the clustering has some advantages. It's not that only because we have to do clustering, we are forced to do clustering. Clustering itself has some advantages. So clustering can be used for finding the features that will be useful later for the categorization. Because by clustering, actually, you will find some similarities between the data points, and you can try to use such similarities to find maybe some new features so that can be represented and as some categorization feature that you care about. So this is why sometimes we just do the clustering and the necessity to do clustering. What is clustering for? Here we provide some real-world examples. For example, when you go to buy t-shirts or any clothes, we know that when we buy the clothes, basically we have different sizes, S, M, L, and possibly XS, XL, some sizes like that. So basically this is already the idea of clustering. So in the clothes industry, they try to group the people of similar sizes together to make some small, medium, and large t-shirts. Use the statistics of the different groups of people and then to make all these t-shirts. Of course, we have to do this because we know the tailor-made for each person is too expensive, right? We cannot just hire some tailor to make the clothes for everybody. And if we just use one size to fit all, possibly it does not fit all. So that's why we just select some groups to represent all the people and then try to make the clothes for the people. Of course, these are only 3 groups. If we want it to be like more detailed or somehow more fine-grained, we can try to make more groups, the XS, XL, some sizes like that. So this is the first real-world example about clustering. Second, when given a collection of the text documents, sometimes we want to organize them according to their content similarities and possibly to produce a topic hierarchy. So note that if we just want to organize them according to their content similarities, actually that's clustering. That's not text classification, right? Because we don't need the labels, the text labels to do that. We only need their contents and then try to organize them, try to group them into different groups and possibly into different hierarchies to do this text hierarchy. That in marketing, that's our first problem shows. In marketing, usually they just segment the customers according to their similarities to do some targeted marketing. So that, okay, now focus on different groups of people. Possibly you can show different advertisements to them. But these are the clustering for in the real world applications. The clustering can also be used to do image segmentation. So what is this? Suppose now we have an image like this, a digital image. Then the image segmentation is we try to partition such digital image into some multiple image segments, also known as the image regions. For example, for this image, if we let the number of cluster to be 5, we will have the image segmentation results like this. So as you can see, roughly actually now we have 5 different groups of pixels, right? So the white one possibly is one group, and the blue one, and also the yellow one, the black one, the gray one. So we try to just separate all the pixels into different regions. If we want this image segmentation to be more precise, we can try to let the number of clusters to be larger. So if we let K be 20 here, the image segmentation results will look like this. So as you can see, compared with this one, actually the imagery now is more fine-grained, more precise. So there are much more different colors and different regions in such imagery. So this is called the image segmentation. All right, so that's some background about the clustering. And of course, clustering is one type of unsupervised learning. If we want to do clustering, basically that means we do not have any labels. We do not have any supervision, just let the machine to find the similarities between data points. So until now, any question regarding clustering? Great, so far so good. So we already know the background of clustering. So for this course, we will only learn one clustering algorithm that is called k-means clustering. So what is that? Of course, unsupervised learning algorithm means that there is no labeled data. It's unlike supervised learning. How would it try to cluster? So it performs the division of data into some non-overlapping clusters that share the similarities. And in the meantime, the same cluster, they must be dissimilar to the data belonging to another cluster. And you may find we have the term K here, like KNN. But even though they both use the K, this parameter, but actually the K has totally different meanings. So previously in KNN, K represents the number of nearest neighbors we use to do the classification, right? That's K used in testing. But here this K, this term K in k-means clustering, is a number telling the system how many clusters you need to create. For example, if we let k to be 3, then refers to 3 clusters. Group all the data points into 3 clusters. So this is the difference. Note that totally different meaning of this term k in k-means clustering. So the algorithm of k-means clustering, first we need to know some the definitions and some terminologies before we apply. So basically, consider we have a set of data points, D, like for example, we have n data points. And then xi, each xi here, know that is a vector. So each xi is xi1, xi2 until xid. This row is the ith data point, or this vector is the ith data point. What is D here? D is the number of dimensions or the number of features attributes. So you can regard this big D, the data points, the set of data points, as a big matrix. So each row, again, is one data point. And each row, the vector represents the data point, contains D features. And that's all. We do not have the labels. Right? It's clustering, it's unsupervised learning. We are only provided with this big D without any labels, only the features. And then to perform k-means clustering, we must first specify the design number of clusters k. Again, we decide k. Tell the algorithm, tell the model what's the value of k. Then the k-means algorithm partitions the given data points into k non-overlapped clusters. A terminology here is called centroid. So each cluster has a cluster center. So in k-means clustering, we call this cluster center as centroid. So basically, we have k clusters is equivalent to saying we have k centroids, because each cluster has one centroid. So this is like some premise of the k-means clustering. And let's look at the algorithm steps. K-means clustering. So given k, k must already be given because we must tell the model what is this k. So given this k value, the k-means algorithm works as this. First, it chooses k, possibly k random data points. We call that seeds because they are like random chosen. Choose this k random data point to be the initial centroids. Recall that initial centroids means initial cluster centers. Because in total, we need k centroids, right? So at the beginning, just randomly choose k. Okay, then goes to step 2. We find the distances between each data point in our training set with the k centroids. So each of the data points, you need to compute its distance with each of the centroids. Again, it's some pairwise distances. One is data set, another is the centroid set, and find the pairwise distances. This step, of course, we should already know like how to implement that, right? If you already know how to implement KNN to compute pairwise distances, basically it's the same here. The pairwise distance between data points and centroids. Then go to step 3. So after you have all the distances, what should you do? You need to do the clustering. Clustering is assign each data point to the closest centroid according to the distance you have computed. This is the step 3. After step 3, note that now the assignment or the clustering results will be somehow updated. After the clustering is updated, the centroids should also be updated because centroids represent the cluster centers. So in step 4, recompute the centroids using the current cluster memberships. So this is your update the centroids. And of course, after you update the centroids, possibly the distances will all change again. So that's why we need to repeat. So it's step 2 to step 4 we call it's one iteration in the k-means clustering. Again, it's some iterative algorithm. So if the convergence criteria is not met, we have to go back to the iterations. We repeat steps 2 to step 4. So basically, it's just we update clustering results and centroids like in turns and just do it alternatively until some convergence criteria is met. So later on, I will talk about what is this convergence criteria. But the algorithm just run like this. So this is the k-means clustering algorithm. Here is a question. It's a machine learning algorithm, right? And whenever we look at a machine learning algorithm, we want to know what steps are training here. What steps are training? Yes?
2 to 4.
Yes, 2 to 4 are training. So basically, yes, the training is just this iterative process. So training means that we go into the iterations and we just alternatively update the clustering, then update the centuries, and then we go back to update the clustering, then go back to update the centuries. The whole training process actually is just the iterative step 2 to step 4. So, actually we can say all of these steps are just training. So basically this algorithm, the steps we listed here are all about training. We haven't go into the testing yet. Because usually for the clustering problem, what we care about is to cluster the training data sets. So usually we don't involve with the testing data. So that's why like a typical k-means clustering algorithm just looks like this. All of them are training, and the results would be the clustering of the training data, right? All of the steps, only the training data are involved. Actually, we haven't seen any testing data. But if you want to apply it to some testing data, it's also okay. So that means possibly after you finish the training, after you finish all the process, after the convergence criteria is met, then you have a new testing data. Then you can try to cluster the testing data based on the centuries. So because at the end, you can have the set of centuries. You have k centuries, right? So then if you have any testing data, you can just try to cluster them according to their distances to the centuries. That's how you apply it to the testing. But usually, we just apply the training for k-means clustering. Usually, we just only care about how to cluster all the training data points. This is the k-means clustering algorithm. Let's try to perform that, okay? Try to perform it in this data set. So again, the same data set we have seen in page 1. We have the more customer data set, 3 attributes here, age, income. The income is in 1,000, and expense score is some more customer data sets. All right, then step 1, randomly pick the data points at the initial centuries. By the way, suppose we haven't seen here. Suppose like we just choose k to be 3. So we just want to cluster all these 20 data points into 3 clusters. So then we randomly pick 3 as initial centuries. We only need 3 centuries. Suppose after randomly choosing, we select the 3 centuries at this 3 1. So if you look at the table, it should be the data point 7 to be the first century, and so on so forth. So each of the data, each of the centuries just come from the original data, and we can also try to visualize all the data points here. So note that these 3 solid points are the initial centuries, and all other gray points are just other data points. This is our step 1. Step 2, find the distances between each data point with the 3 centuries. Suppose now we directly apply Euclidean distance. Of course, it's possible that sometimes we should use other distances, but just now assume we use Euclidean distance. And then we append 3 rows here. Distance 1, distance 2, distance 3. So these 3 terms, dc1, dc2, dc3, are the distances between the data points and the first century, second century, and the third century, respectively. So that means the first data point has the Euclidean distance 62 with the first century, the distance 55 with the second century, and the distance 84 with the third centroid. Note that for each of the data point, we need to compute the 3 distances. So that's the pairwise distance between each of the data point with each of the centroid. After that, we append the table with 3 new rows. Then the next is we should update the clustering, right? We should assign each data point to the closest centroid. So that's the meaning of clustering. Try to allocate the data point to its closest centroids. So basically, is that we just compare DC1, DC2, DC3 and find the smallest distance. Like for the data point 1, we find that, okay, DC2 is the smallest. So that means the cluster of data point 1 should be 2, is closest to the centroid 2. And then for the data point 1, so it's closest to DC1, the first centroid 50 here. So we just cluster it to be the cluster 1, so on and so forth. So for each of the data points, you need to find the smallest distance among DC1, DC2, DC3, and then assign the data point to the closest centroid. So at the end, we have the 3 clusters. So class 1 are the pink ones, cluster 2 are the yellow ones, and class 3 are the green ones. So after that, we have the updated clustering, but it's not convergent yet. So we go into step 4. We need to recompute. We need to update all the centroids using the current cluster membership. So the new first centroid should be, we just look at the table, find all the data points belonging to cluster 1. So that is data point 2 to data point 10 and data point 12. So all these data points belonging to cluster 1 now. So we update the centroid to be the new cluster center. 3 attributes, right? Or it's some 3-dimensional features. So x1 should be like, after you're taking the average, it should be 60.6. And x2, the second feature, now the average should be 42.4, so on and so forth. So after updating, we get, okay, now our first centroid is 60.6, 42.4, 40.9. And the same you can do for second centroid and third centroid. Because the second cluster only have like 3 data points now, so you only get the average of the 3 data points. The third cluster has 7 data points, and you also update to be the cluster center just by taking the average. So after that, actually we have the updated centroids. We are not finished yet. Of course, these centroids already changed, right? If you compare these centroids with the initial centroids here, of course they change. So after the centroids change, then the distances between each data point to the centroids will also change. Then possibly the clustering membership also change. So we have to continue to the next round or to the next iteration. So we omit the calculations here. But we show the visualizations. So this is the first round. First round, our initial centroids are these 3 ones. And we use different colors to represent the clustering memberships. And this is the second round, or after the first round, the new centroids we have computed just now. And according to this set of new centroids, we can update the clustering membership like this. But we are not finished yet. It's not convergent yet, so we need to have 2 more rounds. So after the third round, the centroids will look like this. So if you compare it with the previous one, so this one, you will see that the centroid change again from round 2 to round 3, right? The centroids updated. Then we go to the next round, the first round, and get the updated centroids as well as a cluster membership like this. Until this moment, we can stop. And this also indicated the criteria for the convergence. So that is, if you find that after 2 consecutive rounds, the centroids remain the same. Right? So round 3, and round 4, they have exactly the same set of 3 centuries. So basically that means, okay, the 2 consecutive rounds, the centuries remain the same. They won't get updated, and if they are not updated in 2 consecutive rounds, they won't get updated anymore. Because if the centuries are already fixed, then the distances between each data point to the centuries are also fixed. So the cluster memberships are all fixed, and of course, the centuries will not get updated anymore. So this is one of the convergence criteria. So this is the k-means clustering running results for this example. So it will get convergent after these 4 rounds. And whenever we see that it gets convergent, know that we need these 2 consecutive rounds to show that they are the same. So if you only stop at the 3rd round, it's not correct. Even though the results are still the 3 century, but it's not correct if you stop at the 3rd round, because at the 3rd round, you cannot show that it's already convergent. You still need the round 4 to prove that it's already convergent. Then what is this results telling us? So that is like based on the clustering results, what can we get? What conclusions can we draw? So we can like try to summarize some statistics. The clustering results, we have 3 clusters. The cluster 1 is the 1st century here. So approximately the class 1 average age is 63 years old. The average annual income is $44,000, and the average expense score is 42. This is what we can know about the cluster 1's customers. And cluster 2, the average age is 26 years old. Average annual income is 42,000, and the average expense score is 43. Then cluster 3, average age is 45 years old. Average annual income is 84,000, and average expense score is 19. So if, for example, if you are the boss of this mall, then possibly you can start to design the different marketing strategy or different advertisement strategy to these 3 different clusters of customers, right? So for example, you may already find that, okay, cluster 2, the youngest cluster, who is the poorest with the lowest income but the highest expense score, right? That's the cluster 2. Possibly then you can try to design like the advertisements to targeting on this cluster, because you already know like they have the highest expense score. And possibly you can also try to like design some marketing strategies so that you can attract more of the cluster 3. Because currently you find that, okay, cluster 3 has the highest average annual income, but somehow the lowest expense score. That means they still have like much potential to buy more things because they are very rich. So this is like the conclusions we can draw from the clustering results, and basically that is helping the companies or helping the malls to design the different advertisement strategy to targeting on different customers. All right, so any questions so far regarding this example? Yes, please.
Does the final cluster membership change depending on which distance you allow?
Yes. So we need to select the distance function. So for this example, we just select the Euclidean distance. But if you select some other distance functions, yes, the clustering results will change.
Same for the centuries?
The centuries, yes, will change. Because after like you change, possibly like after the clustering change, of course, the centuries will also like change accordingly. Yes, very good question. So if we look at the algorithm steps here, so it only said that find the distances, but which distance function to use is like, again, we decide. So it's very like the KNN, right? We have to decide the value of k. We have to decide which distance function to use. This is all decided by us. Yes.
How do you choose the initial centuries?
Initial century, usually we just do the random picking. So just randomly select the k centuries from your original data points. Yes. Any other questions regarding? Yes, please.
So will the results be dependent on the initial point?
Yes, yes. Later on, we will talk about that. This is one limitation of K-means clustering. It's very sensitive with the initial selection of the centuries. Yes, very good. Thank you. Any other question regarding the K-means clustering algorithm and also the example we just worked on? Yes, please.
For the centroids, we have to choose them somehow equally distanced within the range of the data, so it's more or less even distribution.
Actually, not necessarily. Still, it's possible that it depends on like which direction you are choosing, like the distance, because usually the data is like multi-dimensional. So if you choose like in different dimensions, like the distance, then possibly the results are still very sensitive. So the clustering results may still like change. Yeah. Yes. So this is the limitations of K-means clustering, and in order to like try to solve this problem, like it's very sensitive to the initial centuries. So actually, usually when we do the K-means clustering, we will select different sets of initial centuries. So that possibly we will run multiple K-means clustering. So with like, for example, the first run, we select one set of random initial, and then the second run, we select another groups of initial centuries, and to see like which one is the best. Yes, thank you for your questions. Very good. Any other question regarding this example and the algorithm steps? Yes, please.
For recomputing the centroids, is finding the mean the only method?
Actually, not. Very good question. Yes. Usually, we just find the mean because the centuries it represent cluster centers, and usually we know that the center is the mean, but that's only holding true in Euclidean space. So if we are working on some different spaces, then the mean is not the center. Actually, I know that possibly like all you know about the space is the Euclidean space, but actually there are some other spaces in mathematics like the hyperbolic spaces. In hyperbolic spaces, the center is not the mean. Actually, the mean is not well defined in hyperbolic space. You should define some other metrics. Yeah, but that basically that's some like geometry knowledge. So we won't cover here. So in this course, we only consider the mean is the center. So we only like assume that we just work on the Euclidean space. But very good question. Thank you. Yeah. Any other questions? Yeah, very good. So actually, all of your questions, try to like underline the assumptions of the K-means clustering, and you already pointed out many like limitations of K-means clustering. For example, the initial centuries. Yes, actually, K-means clustering very sensitive to initial centuries, and the distances. Yes, K-means clustering can choose different distance functions depending on which types of data you are working on. Basically, the rules follow what we already talked about in KNN. In KNN lectures, we introduced like different types of distance functions, and at that lecture, we illustrated like which data point or which cases some distance functions are preferable than Euclidean distance. All of those conclusions actually also apply here. Basically, it depends on like which type of data you are working on. And centuries and cluster centers, very good question. Yeah, so actually that's indicated the assumption of the centuries. So when we're saying that the centuries, we want to compute the century using the mean, then we already assume that the K-means algorithm works in Euclidean space. Actually, that's also another limitation of K-means clustering is that if the data, they lie in different spaces, if they are not in Euclidean space. So for example, they possibly like in hyperbolic spaces, in some complex spaces. In that case, the cluster centers are very hard to define. So not as easy as in Euclidean space. So yeah, very good questions. So next, let's see how to implement using scikit-learn again. In lab 4, by the way, lab 4 is already released. Yeah, later on I will just make an announcement today. So lab 4, you need to implement k-means clustering from scratch using NumPy. So here we just show you how to implement using scikit-learn. All right, so NumPy, we always need that. And then we import the modules k-means from scikit-learn.cluster. And in order to do some visualization, we also import this matplot library, .pyplot as PLT. This is a very, very useful, very powerful library. Basically, all of like the machine learning or the AI algorithm, the results can be visualized using this library. So very good one. Yeah, later on you will see how to do that. Then we first form our training data. Our training data is some unlabeled training data. We only have the features. So we formulate it as a 2D array. So with the shape 20 that we have 20 data points, 3 that we have 3 features here. And then initial centuries, we just set it to be this another 2D array. As you can see, the shape is 3. The first three rows mean that we have 3 initial centuries. That's the k value, big K value. And the column 3 means that we, again, 3 features. So this is the initial centuries. We just pick it up. After that, we create the k-means object from the scikit-learn module here. Yeah, as you can see, actually there are like multiple arguments here. I try to explain them one by one. N clusters, this is easy. N cluster is just the big K, right? So we set N cluster to be 3, and then init, let it to be init centuries. Init centuries, which we formulated here. So we directly pass all randomly picked initial centuries to the init to indicating we want to select these 3 points as our initial centuries. Later on, I will also explain what if the init be other values. Actually, it can be other values. And uninit, this one, we let it to be 1. So what does it mean? So this means the number of times that the k-means algorithm will run with different cluster seeds. Actually, that corresponds to your questions previously. So if we choose different set of initial centuries, actually the resulting membership will change eventually. So to avoid that, it's very sensitive to initial centuries. The scikit-learn's k-means actually provide such implementation so that you can run this k-means algorithm with different century seeds to run it multiple times. So this uninit, you can let it to be larger so that actually it will select different sets of initial century and run different times. But since now we directly specify the init to be the init centuries, it's already fixed. It must be fixed as this one we formulated it. So the uninit, we just let it to be 1. Only need to run it once. And the max iteration, of course, it's the maximum number of iterations you want it to run. So basically, we know in the algorithm, step 2 to step 4 is 1 iteration. And just previously through our manual calculation, we have seen actually it converged after 4 iterations. So yeah, we directly let this max iteration to be 4. Then I would like to talk more about what is this init and what is this uninit. So in order to know that, we should always look back to refer to the documentation. So next, let's check the k-means clustering documentation. Okay, so yeah, look at this documentation. Actually, it has like multiple arguments. So usually we only use this n clusters K, and this init, n init, and max iteration. Usually we only use these 4 arguments. So let's check what it is init. So this init, it can be k-means plus plus, or random, or some callable or array-like of this shape. Note that in our case here, we select it to be an array-like of this shape, right? So that means we indicate what are the initial centuries. But what it means if we let init to be k-means plus plus. So k-means plus plus means that it selects the initial cluster centers using the sampling. The sampling is based on an empirical probability distribution of the points contribution to the overall inertia. Later on, we will also talk about what is this inertia. It's a metric. Why sometimes we use this k-means plus plus? So basically, that we want to speed up the convergence. So by selecting a good set of initial centuries, actually it will speed up the convergence because it's very close to the true centuries. So if we use these sampling methods to just draw these centuries, speed up convergence, and this algorithm actually is using some greedy algorithm. If you have learned the algorithm, you probably already know what is the greedy algorithm. So this is for the k-means plus plus. Use some more advanced empirical methods to do the sampling and then select the centuries. And of course, we can also let it to be random. Let it to be random, then basically it means that we want the k-means, this module, to choose this big K observations at random from the data. So let it to be randomly picking up. And if an array is passed, just like how we use that, then it should be in this shape and give the initial centers. Actually, it can also be a callable thing. What is a callable thing? Callable means a function. So this argument init can also be a function, a callable function. If this is a function, then it should take the arguments big X, n clusters, and then a random state returns an initialization. So basically that if you have another random function, or if you implemented some random function, you can just use that random function to select the initial centuries for you. So it can be these 4 different types, the initial, the init. Then let's see what is this n init. N init, it can be auto. If you are not sure which to assign, you just let it to be auto. Or it can be an integer. So the default value is auto. So this is the number of times the k-means algorithm is run with the different centroid seeds. And then the final result is the best output of n init consecutive runs in terms of inertia. So inertia is a metric which we will talk later. So basically, you can regard inertia as an evaluation to evaluate the clustering quality. So it will select the runs with the best clustering quality. And the several runs are recommended for some sparse high-dimensional problems. If we set n init to be auto, the default value, then the number of runs actually still depends on the value of init. If we let init to be random, so if we let this module k-means to select the random initial centuries, then by default, n init is 10. So it will run 10 k-means clustering algorithm with 10 different sets of initial centuries and then select the best one with the best clustering quality. But if init is k-means plus plus or init is some array-like, then the initial centuries are fixed. So actually the init is just 1 because no need to run so many times of the k-means clustering. So this is the meaning of these 2 arguments, init and n init. So from this arguments, the documentation description of these 2 arguments, so possibly you can already see that the safe way to perform k-means clustering so that you can select some good centuries. The first is by sampling. So this is using this k-means plus plus. Usually by this way you can like select some good choice of the initial centuries. The second way is that you use random. You randomly choose the initial centuries, but you run it for multiple times. So for example, run it for 10 times and then select the best one. That's it. Try to solve the problem of k-means clustering that is very sensitive to the initial centuries. All right, so any question related with these two arguments, the init and uninit? Great. So for our example, since we just use the 3 centuries that we randomly picked, and we want to like just indicate we want to use this one, so uninit is just 1. All right, and then next fit is train, right? We use this object we just created k-means.fit data. Data is the training data we formulated here. So this is just we directly go into the training. By the way, what happens inside this fit function? So after we run this one, what is this function doing? So it will perform the computations we have manually done before. So it will compute the iterations, right? So it will iteratively compute the distances, assign the data points to different clusters, and then recompute the centuries until the stopping criteria. So in this case, the stopping criteria is indicated here. We already set the max iteration to be 4. So after we run this k-means.fit data, it will just run these 4 iterations, do these iterative computations. And after that, we can try to see the clustering results for the training data. We use these labels equal with k-means.predict data. So this predict is predict the closest cluster for each sample. And after that, we can try to print out these labels. And we can also get the centuries. The centuries is the object instance variable. So let centuries be k-means.cluster cluster centers. Then we will get that after convergence, after stopping, what is the resulting centuries, the last centuries in the last iterations. And the next thing is that we try to visualize the whole the whole results, the clustering results. So basically, these are just setting for this matplot library, setting, create some figure, and then create the axis. And note that here we need some 3D axis because the data are in 3D space, right? We have like 3 features. And after that, we get this Boolean arrays representing the 3 clusters. So basically, A is that numpy.array labels is 0. So we select all the data whose like label is 0, and B is label is 1, C is label is 2, the 3 clusters. And after that, we can still like setting all these things. So we use different colors. Like here, we use the black to represent the centuries. And we use red to represent the first cluster data points, green the second cluster, and blue the third cluster. After you're setting all the labels for each of the axes, like we have like 3 axes, you can get the visualization results. The visualization results are already here. Basically, all these 4 figures are drawn using the codes here. So eventually, you should get some results like this. And note that since we already indicated the initial centuries, so these results, like after you get the prediction, the predicted labels and centuries, they must be the same with our manual calculation, because the initial centuries are the same with our manual calculation. So we select the same set, so the results must also be the same. But if you select if you let the init to be random, then it's possibly you will end up with different clustering and different centuries because it's like sensitive to the initial centuries. All right, so any question related with the implementation using scikit-learn? Great, so yeah. if you use scikit-learn, again, everything will be quite easy. Basically, you only need to know what these arguments mean and assign the correct values for these arguments and then directly call all the methods. All right, if no question, then let's take a 5 minutes break. After the 5 minutes break, we will continue to do some analysis on the k-means clustering. All right. Yeah. Let's come back to the class. So until now, actually, as you can see, the K-means class 3. Again, the steps are really straightforward. It's a little bit like the KNN. So that's why in previous semester, usually some students will get confused between these two, like the KNN and the K-means class 3. But you need to, definitely you need to distinguish these two algorithms. They are two totally different algorithms. KNN is for supervised learning. K-means clustering is for unsupervised learning. They are totally different, but the steps are really straightforward, and actually these share similarities in the steps, right? Both of them actually need to compute the pairwise distances, but in KNN, know that the pairwise distance is computed between training data and testing data. Because for KNN, we only do the pairwise distance computation when we do the testing. But for K-means clustering, the pairwise distance is computed between training data and centroids. So that's the difference. And also, the K has different meanings. So first, let's check the K-means stopping criteria. We already know the steps of the K-means. Actually, it should stop after some, convergence criteria is matched, so we introduce them. So the first is that if we find that there is no reassignments of data points to different clusters. So basically that is the clustering membership remains the same in 2 consecutive runs, and then it gets converged. This is the theoretical stopping criteria or stopping convergence. This theoretical convergence criteria is that no reassignment, but in practical, usually for efficiency, we also accept that if there is just some minimum reassignments. But note that for the minimum reassignments, possibly we call it stopping criteria. Because theoretically speaking, it may not converge yet, but in practical, just to save the computation time, we can stop it earlier and set this stopping criteria as some minimum reassignments. Equivalent criteria is that no change of centroids. So no change of centroids is equivalent with no reassignments of data points. So basically, in 2 consecutive runs, you can either compare the cluster membership or you can compare the centroids. If you find that any of them remain the same in 2 consecutive runs, the other must also remain the same. Right? If the centroids remain the same, of course, the distances should remain the same. So the cluster membership remain the same. Or if you already find that the cluster membership remains the same, then after you're taking average to get the centers, of course, the centers should also remain the same. So these first 2 conditions, they are equivalent with each other. We have a third one of the stopping criteria. The minimum decrease in the sum of squared error, SSE, between some successive iterations. What is this SSE? So SSE actually K-means clustering, even though the steps we have seen are quite simple, quite straightforward, but all of the steps, they are trying to minimize one error, this sum of squared error. So actually the ultimate goal of K-means clustering is just try to minimize this error. So K-means clustering has error function, and it always try to minimize this error function. We won't provide the mathematical proof that why those steps will minimize this SSE, this error function. If you are interested actually in later on in COMP2211 Fundamentals of AI, that course will teach you why to minimize this SSE will result in the algorithm steps. But until now, you only need to know that actually we are trying to minimize this error SSE. Okay, SSE, some nasty sum. So it's the sum j from 1 to k, this case, sorry, it should be the big K. So that is for all the clusters. And then for all the data points belongs to the cluster J, we get the sum of the square of distance. So distance between x and mj square. So here Cj is the j's cluster, and mj is the centroid of cluster Cj. Then the distance x mj is the distance between the data point x and the centroid mj. So then what it tries to minimize, basically it tries to minimize that for each of the cluster, we find out all the data points belonging to that cluster, right? So find out all the data points x belonging to this cluster Cj, and then we try to compute the distance between this data point to its centroid mj, and then get the square of the distance, add them up. So this SSE measures, basically tries to measure, roughly speaking, tries to measure the distance between each data point to its assigned cluster's centroid. Minimizing SSE means that we want all the data points are very close to their centroids, right? Only if all the data points are very close to their centroid, this SSE will be very small, will get minimized. So this is the meaning of the SSE. So now that we know there is a loss function or an error function in k-means algorithm, and convergence criterion is that at some point we reach the minimum point of this error function. We reach the minimum of this SSE. But does it guarantee to converge? So, like after each iterations, will the SSE guarantee to decrease instead of increasing? Actually, yes. The proof, I think in the Lab 4 review notebook, like the TA provided a rough proof, a sketch of proof. Actually, yes. So that means in k-means clustering, it's already guaranteed that in 2 consecutive iterations, SSE must decrease. Like in later iterations, SSE must be the smaller than the previous iteration, and k-means clustering is guaranteed to converge. So that means it's guaranteed to get to some local minima of SSE. Local minima, not the global minima. So it will converge, but k-means is not guaranteed to converge to the optimal solution. Not guaranteed to converge to the optimal clustering results, but it will definitely converge to some local optima. And you probably already know which optima to reach depends on your initial centroids. If you select a very good initial centroid, then possibly it will just converge to the global minimum. But if you select somehow some bad initial centroids, then possibly it just converge the local minimum, but still it's converged. So no worry, it will guarantee to converge. The SSE will definitely get decreased. So theoretically speaking, this is the true convergence criteria. That is reach the minimum point of SSE. But still we can try to like get the convergence criteria referring to the first 2 conditions, because actually they are just all equivalent with each other. But this is like more theoretical. This is the true loss function, but the first 2 are some like behaviors of the k-means clustering algorithm. These are the stopping criteria. And of course, in practical implementation, a more practical way to set the stopping criteria is to set the maximum number of iterations. Right? So like previous implementation, this one, actually we just set the maximum number of iterations to be 4. This is a practical way. This is a stopping criteria. You can stop your algorithm when it reaches the maximum iteration, but it's not convergence criteria. So it's possible that after it reaches the maximum iteration, still the algorithm has not converged, but we don't want to waste our computation power, so that we just stop at this maximum iteration. All right, so any question regarding the k-means stopping criteria? Okay, great. Then some common questions about K-means clustering. First of all, how to choose K? Because we still meet the same question with K and N, how to choose this K, right? The answer actually, in K and N, we know that we can use the default cross-validation. Default cross-validation is that we have a large training set, we just split it into defaults and always do the validation to measure the errors to select the K with the smallest error. But now, usually for clustering results with clustering algorithm, we don't do that because the evaluation metric is not so accurate because anyway, we don't have the true labels. So for K-means clustering, we have some different methods to find the optimal value of K, like the elbow method and the Seeholt method. So these methods we will be discussed in some advanced level machine learning courses. So here we just omit them, but there are indeed some methods that we can select the number of clusters. We can choose the K, the good K value. Second question, what distance metric should be used for K-means? Of course, depends on your data. Just like for K and N, there are different choices, Manhattan distance, cosine distance, and Hamming distance, right? So which distance basically depends on your data, which distance your data shows the best. But normally, K-means uses Euclidean distances because it's very convenient, and in most of the cases, the data are naturally captured using the Euclidean distance. Next question. Do we need to standardize the data before doing K-means clustering? Like in K and N, we do data standardization, right? It's like one more step of data pre-processing before we apply K and N. Actually, yes. Actually, for K-means clustering, we also need to do the data standardization. So actually, in our previous manual calculation, it's not so sound because we haven't do the data standardization. Like previously, the income is in the units thousand, right? The $1,000. What if the income is represented using the units of dollars? Then the income will just dominate the Euclidean distance calculation. So that's why we always need to do the data standardization if our algorithm depends on the distances. Like K and N depends on the distances to make prediction, and our K-means clustering also depends on the distances to do the clustering. So for such distance-based algorithm, we always need to do data standardization before we apply K-means. So the most sound way is that first data standardization, then apply K-means clustering. Yeah, due to the fact that we know such distance-based measurements actually possibly different features, they are in different scales and they are not so comparative with each other. The next is about the clustering quality. Know that usually for clustering we don't see the error measurements. Even though we have SSE, but SSE is just roughly capturing the clustering quality because we don't have the actual labels. So we can never measure the true error, right? We don't know which of the data points should belong to which class. So we can only try to capture what is the quality of clustering. And for clustering, usually we have these two standards to say what are high quality clustering. The first is isolation. Isolation means we try to maximize the inter-clusters distance. So that is the distance between clusters. So if we look at this sketch, so suppose we have 3 clusters here, and this red point, these black points represent the centroids of the clusters. Then inter-cluster distance is this big L. So this big L is the cluster distance between cluster 1 and cluster 3. So this is the inter-cluster distance. So we want to maximize this inter-cluster distance means we want to make sure that the different clusters, they are far away from each other, right? So this is called the isolation. That means the cluster should naturally capture that. So the dissimilar data points, they should be assigned to different clusters. Try to maximize this inter-class distance. In the meantime, we have the second standard of the quality is called compactness. Compact means that we want to minimize the intra-class distance. So that is the distance between data points in the same cluster. Usually we just use the distance between the data point to its centroids to measure this intra-cluster distance. So here this small d is intra-cluster distance. So the distance between a data point to its centroid. We want to minimize such intra-class distance, mean that we want to make each cluster as compact as possible, so that all the similar data points, actually they should belong to the same cluster. So if you look at the how to measure like the quality of clustering, you will find that actually we have two goals here. The first goal, we want to make the similar data points in the same cluster. The second goal is that we want, in the meantime, we also want the dissimilar data points in the different clusters. So that's by maximizing inter-cluster distance and in the meantime minimizing the intra-cluster distance. And know that usually the quality of a clustering algorithm of a clustering results depends on the algorithm itself, and also it depends on distance function. Because when we try to maximize these distances, try to minimize these distances, it depends on which distance function we selected, and also it depends on the application. So that is like in which scenario you want to apply your clustering tool. So these are the clustering quality. So yes, please. Maximize what? Sorry.
The intercluster naturally gets maximized at the final round of iteration.
Yes, it's not, actually these metrics are not applied in the, actually this one will apply, but the intercluster is not applied during training. It's only after the clustering results we use these two standards to try to like evaluate. But yes, that means after the final iterations we get the clustering results and then we use it to measure. Yes. But actually this intra-cluster distance will be applied in training if you still remember here. If you still remember the, yes, the n init. When n init is larger than 1, then several runs, actually they are just running, right? Several algorithms is running in the same time, and it will get the best output of n init consecutive runs in terms of inertia. And actually this inertia is the intra-cluster distance. So it will, like the scikit-learn's k-means module will try to get the best result according to the inertia here. Yes, very good. Any other question regarding the clustering quality? All right, then, yeah, the weakness of k-means. Actually, through your questions, basically you already identified all the weaknesses of k-means. Very good. First, it's very sensitive to outliers. So outliers are data points that are very far away from other data points. For example, possibly this is an outlier. And usually this outlier, they're just some errors, some noise in the data recording or some special data points with very different values. If we have the outliers, it will definitely affect the clustering results. And possibly we will get these undesirable clustering results. So naturally, we should cluster them into these two clusters, right? This is our desirable clustering, and then we just identify this as an outlier. But if we ignore the outlier and put it also into the clustering algorithm, we will end up with the undesirable clustering. In order to accommodate this outlier, actually these 4 points will also be clustered to the left cluster, so which is not so natural clustering results. Then how to deal with this outlier? Like how can we spot this is an outlier and we just should kick it out? So there are some ways. We need to remove some data points in the clustering process that are much further away from the centroid than other data points, because possibly these are outliers. For example, you may find that all the data points they are just the distance to some centuries are just maybe 10, 20 something. In the meantime, there is one data point who has the distance like 1,000 to all other centuries. In this case, possibly that's an outlier. It's very far away from all the centuries than other data points. But to be safe, we may want to monitor these possible outliers over a few iterations and then decide to remove them. So like in some consecutive iterations, you find that, okay, this point is always very far away from all the centuries, then possibly it's an outlier, you can remove it. This is the first way to deal with the outliers. That is, during the training, you just monitor all the training process, monitor all the distances you have computed, and identify outliers, remove it. Second way is you can perform some random sampling. Because in sampling, we only choose a small subset of the data points, then the chance of select an outlier is very small. So in this case, from a big training data, you do random sampling, sample a small data set as the training, and you train on that small set. Then what about the testing? You can assign the rest of the data points to the cluster by distance or by similarity comparison or classification, because after you train the small training data, you already have the classing results, you already have the centuries, and you can assign the remaining data according to their distances to the centuries. So this is how to deal with the outliers. Another weakness, you already know, very sensitive to initial seeds. Know that if we use the seeds that are not so good, we will end up with not so good results. Like if we have the data sets like this, the natural classing one should look like this, right? So that we just separate them into two groups. Like if we select the centuries, like one is here, then we will end up with this good results, the good classing results. But if somehow we select not so good initial centuries, if we select one century here, and possibly one century here, then at the end, possibly we will just end up this classing results. So the classing actually will change depending on the different selection of the initial seeds. So that's why the scikit-learn's k-means module implemented the n-init. So that's why it will select different sets of initial century and then run the multiple k-means clusterings. Another weakness, this is I think this is the most significant one, which highly limits the usage of k-means, is that k-means algorithm is not suitable for discovering clusters that are not hyper-ellipsoids or hyperspheres. If we look at this data set, we know there are two natural clusters, right? This should be one cluster. This should be another cluster. There are two natural clusters. But if you use k-means clustering, you will end up the results like this. It will try to cluster the data point into two very unnatural clusters because k-means clustering algorithm cannot deal with such shaped data set. Or basically, the k-means clustering can only deal with some linear data sets, cannot deal with some non-linear data sets like this. So this significantly just restrict the k-means applications. It can only deal with some types of data, and when the data are too complicated, simply the k-means cannot produce any reasonable results. These are the weaknesses. Alright, so we already run out of time, so let's end up here, and next class we will continue to introduce the pros and the cons and k-means classing, and see you in next class.